Hi everyone, this is Sushma. In this video, I'm going to talk about one of the cost effectiveness analysis approaches. In the field of public health, one frequent question that we come across is the new intervention B more cost effective than the alternate intervention A? This is such an important question in a resource constrained setting, and the answer to this question can guide the researchers and policymakers regarding the decision on whether or not to choose an alternate intervention compared to the existing intervention. Some of the common approaches to answer this question is by estimating incremental cost effectiveness ratio, also called ICER, and incremental net benefit. It is another approach. Uh, and usually both of them are presented together. In this video, I'll present you what is ICER and how ICER and its 95% confidence interval can be calculated using person level data in our software. For the second measure, please stay tuned for my next video. And if you find these videos useful, don't forget to subscribe to our channel. So, what is ICER? ICER is the difference in average cost of two interventions uh, divided by the difference in average effectiveness of these two interventions. And the cost here is expressed in monetary terms. For example, it could be US dollars, while the effectiveness is expressed in health utility terms such as number of lives saved, new cases of HIV diagnosed, years of life added, etc., depending on your research area. And it is commonly expressed as delta C over delta E. So ICER is basically the additional cost required for an additional effectiveness for the intervention B compared to intervention A. So ICER can fall in one of the four quadrants is shown here in this figure that I borrowed from this editorial, published editorial. It's very interesting and nice paper. You can refer to this paper if you want to read more details about this. But I'll tell here in short, if ICER value could fall in any one of these four quadrants here, the northeast, northwest, southwest, and southeast. If the ICER value falls in the southeast quadrant here below on your right, it would mean that it's negative, and that would mean that for each additional effect gained, there is less cost for new intervention compared to the older one. So we would right away might be right away we would accept this intervention because it's more effective but at the same time less costly than the existing intervention. By contrast, if the ICER falls in this northwest quadrant here on the top left, it would mean that the new intervention is more costly and at the same time less effective. So we would reject this intervention. Now let's talk about the north, east, and southwest quadrant. So if the ICER value falls in the northeast quadrant here, that means the new intervention is more costly, but it's more effective also, which is like for most of our intervention that we study. However, even though it is more effective and more costly, whether or not we want to accept this intervention would depend on our willingness to pay. So if we are willing to pay more, then for the more effect, we might be paying more. Likewise, for the ICER value in the southwest quadrant, uh, that would mean that there is less cost for a loss in health utility. So there is a potential there to accept the intervention if it is cost saving based on how much loss in health utility that we are willing to accept. Yeah. So finally, to estimate the uncertainty around ICER, we could use Feiler's theorem, which is a parametric approach, or we could use non-parametric bootstrap approach. So with that brief background, now let's move to my R window to see how we can do this analysis in R software. So now let's look into my R Studio window. So here, first of all, I'm loading different libraries and install required packages using the Pacman package manager in R. So let me do that here. I'm loading different packages here like datasets, Pacman, Rio, Tidyverse, and all. So you can read here what are the purposes of those packages and libraries. And then once that's done, I have set my working directory here, and I do have the data in a CSV format with cost and effect data for 50 individuals in intervention A and 50 in intervention B. So I'm loading that data here. So you can see in this data set sections here, you can see there are 100 observations of 4 variables. So let's see what are those different variables in there. So here you can see that there are 4 variables: person ID, intervention cost, underscore USD, and effect. So intervention is saved here is an integer. So let me change it to a factor. I'm doing that here. Now let's look into the data. Yes, now we can see the intervention 0 is recorded as 0 and 1, and it has now been converted to a factor. Now let's quickly see the summary measures for each intervention group. For now, let's just check the mean and standard deviation. So I use this group by option, group by intervention, and let's see the summary. And here we can see that there are 2 interventions, 0 and 1. The mean cost for intervention 0 is 2,518, whereas for intervention group 1 is 2,939.79. And we do have the standard deviation for cost, and likewise the mean year. Year here represents the effect variable. So the mean years of life saved, let's say, is 2.10 for intervention group 0 and 5.48 for intervention group 1. That's quite a difference in there. And the number of observation we can see here is 50 for each intervention group. Now let's also check the box plot to see if there are any outliers that we need to take care of. So I use the ggplot function here and geom box plot, and here in the plot section we can see that intervention group 0 is represented in the first box plot and intervention group 1 is in the second box plot, and we do not see those sort of like extreme outliers that we should be concerned about. Looks good. Now let's also do the same for the effect by intervention. So this also looks good, and our dataset is now ready for some further analysis. So, as mentioned earlier, ICER is basically delta C by delta E. So, to get the delta C, we basically we regress the cost on intervention. We could use a standard linear regression of this format, or we could use the model that gives us robust standard error. So for this purpose here, I am using the unequal variances linear regression using the GLS function here. You can see. So first I regress the cost UST underscore UST on intervention. Let's run that. Let's see the summary. Here we can see the variable intervention 1 has this value here, coefficient, which is our delta C. And this is the standard error of delta C. And we have the 98 degree of freedom here. We do the same for effect model. I regress effect on intervention here. Let me run this and then see the summary. The coefficient for the intervention variable is 3.38 with 0.118 standard error. And then the degree of freedom is same for both the models. And here so earlier I did not do this, so let me run this part. So here I am basically saving this delta C coefficient of the intervention variable is delta C DC. We run this, so we have saved it here. And then similarly I do the same for the coefficient of intervention variable in the effect LM model, and I saved it here is DE. And then ICER is basically delta C by delta E. So we have our ICER there. It's 124.72. So that basically means for an extra year of life saved, we need an additional cost of 124.72 US dollar for intervention 1 compared to intervention 0. So now to estimate the 95% confidence interval using the parametric approach, the Feiler's theorem method, we need to do some grabbing of different coefficients first. So we need the delta C square, which is basically the square of delta C that we just saved earlier, and then we also save the standard error of the delta C. So that is basically the standard error of this intervention variable in the cost ELM model. And then the degree of freedom, we have that. Likewise, we do the same for the effect model. The DE square, DE2, we save the square of delta E squared, and then we save the standard error of the intervention variable in the effect model as DESE here. And then let's do some calculation of correlation and covariances for the intervention group 0 and intervention group 1. So to do that, I use here group by intervention and then save some summary measures. So here core cost effect is the correlation of cost and effect, and then CSE is the standard deviation of cost, ESE is the standard deviation of effect, and then N is the total number of sample for each of these levels of intervention. And then covariance is basically this correlation multiplied by standard deviation of this two measures, two variable cost and effect divided by the sample size. So let me run this. And then we have saved these different estimates here by the intervention. So when we click on this, we can see for the intervention group 0 and intervention group 1, we have the correlation of cost and effect, standard deviation of cost, standard deviation of effect, and the number of observations, and then we do have the covariance for each of them. So now we estimate the total covariance for the intervention group 0 and intervention group 1 by adding the covariance of these two levels of intervention that we just calculated here. So the covariance, we saved it as COV, and then we can calculate the correlation between delta C and delta E is the when we divide covariance by the standard error of delta C and delta E. So we can now save the CORR correlation here, and then here we estimate the critical t-value by using this inverse cumulative density of a student t distribution for the given degree of freedom that we have already saved it in the earlier step. So let's do that here. So our critical t-value is minus 1.98, and now here comes the key step where we estimate different values that are required to estimate 95% CI using the Feiler's theorem. So here I have saved measure EMM, which is basically the a product of these two point estimates, delta C and delta E. And then here we perform some corrections using t-square and the correlation between delta C and delta E, and we also take into account the standard errors. And we save it as EMEM, and then we have another measure here, NN, that basically incorporates the uncertainty in our numerator, in our denominator, dE square minus t square times the standard error, square of the standard error of dE. And likewise we have saved here OO, which is the similar measure, but that's for the uncertainty, that incorporates the uncertainty in our numerator, delta C. And here we now can calculate the 95% confidence interval for our ICER, which is a ratio in itself, and the formula follows this sort of this so this is the formula here. So that's basically EMM plus minus square root of EMM square minus NN times OO divided by NN, and these values we all calculated all of them here in the earlier step. And now we can simply use EMM minus square root of EMM square minus NN times OO divided by NN for our lower limit of 95% confidence interval. Sorry, I did not run that earlier, so let me run them. And we have that, and then likewise we do the upper limit estimation using the plus sign here instead of minus. And then let's do some. Now let's see what is our lower limit of ICER. It's 91.45, and the upper limit is estimated as 159. And let's look into our ICER again that we had calculated. So ICER is 124.72, lower limit of ICER is 91.45, and the upper limit is 159.06. Now we can make some plots for the visual. So let me do that here. So I'm using the ggplot. So geom AB line defining the slope is ICER, and then for lower limit here and for upper limit, and then we can fix the geom point at delta C and delta E, and then let's run this code, and we can see here our additional effect and additional effect in the x-axis and additional cost in the y-axis, and here the red dot is the ICER value, and the green one is the upper limit, and the blue one is the lower limit of ICER. And if you would like to make it more informative, we can also add 95% ellipse, and to do that I specify here theta with a length out of 1000, assuming that will be enough to create an ellipse, and I calculate the 95% ellipse and the points along the 95% ellipse, and I do the same for the 50% ellipse and point along the 50% ellipse. And when we're doing the plot here, we additionally we just add the geom path for this 95% and 50% ellipses here. And when we run this, we see a beautiful plot here on the right, where we can see the ICER and surrounded by the 50% ellipse shown by the dashed line and 95% ellipse shown by the solid ellipse. This is how we can do it. I hope you liked the video. Stay tuned for more. Thank you.